that can't be valid. Okay, so reliability is you're basically you're measuring what you want to measure, right? So if you've got the 30 item scale, and the scale is tied to, say, like the DAST or MAST, you would expect that how the person scores across items, or let's say it's should be relatively consistent, right? So there should be consistent patterns in how people respond. So, and if you're tapping into the same, and for your, like, say the scale taps into a common concept or construct, let's say it's procrastination, you would hope that there'd be a fairly strong correlation amongst the items for procrastination, right? So if a person, and they should cluster fairly well. So there's different ways in terms of reliability, in terms of people answering in a consistent manner, right? So a consistent manner could mean you do test retest. So you give the people the instrument, they fill it out, you get their test score, their scale score for, say, depression or whatever, and then you assess them maybe a week later. Now their symptoms may have changed, but that's depression is probably not the best example. The procrastination would be the better one. So you measure them on procrastination 1 week, and then a couple weeks later, nothing's changed in their lives, they're just doing it with a routine. You reassess them again and on procrastination. And if your test results are consistent and valid, they should score the same between the two test periods, right? So the test and then the retest. And the correlation should be high. You should have inter-item, in terms of reliability, the patterns that you see in terms of items. If some items correlate well together because they're clustered together and consistent, you should see those correlations exist across people, right? So if they answer yes to one question and they typically answer yes to another question, those patterns, they should occur consistently. And also you can do a rater reliability in terms of, so this would be more, this is something that you would do in, if you're doing qual research. I don't know if Magda talks about this, and you have to do qual research and you're doing, you're transcribing a video session. So you have like you have your coding manual for the coding of actions that you're observing in the video. And what you would want to do to assess the validity, reliability of your coding scheme is you have multiple people do the coding. And what you would hope is the patterns in terms of how they code it for the video that they're observing, they should be reliable, right? So it should be like people should score it the same way. So if you have inter-rater reliability, that means that multiple people scoring the same videotape in terms of a coding scheme should code it the same, right? They should coding pattern. The coding should be fairly close, or if not the same. And the more consistency in terms of coding between raters, the more reliable your measure, and it's one step towards determining in terms of the evidence that it is a valid measure, right? So if it's reliable, thank God, we then may have a fairly valid coding scheme. If you find that if you have multiple raters and they're not the same and they're inconsistent, then you clearly don't have a valid coding scheme because your raters can't even code it consistently. Okay, so let's say the example we're going to use right now is that we'll do the test retest. I have booked I've booked the hands-on lab for those who particularly for the Mac users who need SPSS if they want to run through this, and also for those who don't just prefer to use hands-on as opposed to the apps anywhere on their own personal computer. So to measure the relationship between in terms of test retest, if your score should be consistent. So if you score high during the one administration or the one test, you should also score high on the retest. If you scored low on the test, you should score low on the retest. So what you expect is a positive relationship between the score on the test and the score on the retest. So just for a quick review, this is just to go through the correlation coefficient. And as you know, the correlation coefficient is a metric that measures the relationship between two measures. So the measure we have here is weekly food store spending, how much they spend in grocery stores, and weekly restaurant spending, how much they spend in restaurants. Right. So this is an example from stats, and I want to see what is the relationship between the two. If they spend more on food in the grocery store, do they also spend more or less at the restaurants? Right. Intuitively, you think if you buy more groceries, that means you're eating in more. You should spend less in restaurants. Right. So the higher your food store, your grocery store bill, the lower your restaurant bill should be. But not necessarily, as we'll see. Okay. In terms of a visual, the visual that I use is the scatter plot. Right. So here are the people in the population member. Right, this is all the Match-A-Dash people. So here's the population. It's all 10 remaining Match-A-Dash people under 30 or whatever. Here's what they spent on here's what person one spent at the grocery store that one week. Here's what they spent at the restaurant. So if I look at the person who spent spent $250 in $220 in groceries and roughly $150 at the restaurant. So what you do is that person's point, and Excel SPSS will generate this for you. If I go down from this person here straight down, it'll take me to what their weekly food spending amount was. So straight down to the horizontal axis says that person spent $220 at the grocery store. And then if I go across to the vertical axis is how much they spent at the restaurant, right? So each point here in this two-dimensional plot with an x-axis and a y-axis, the x-axis is for each point. I go straight down, how much they spent at the grocery store. And for that point, if I go across, it says how much they spent at a restaurant. Okay, so that's kind of, and then what I want to see is, there's the direction of the relationship. So those who spent little at the grocery store spent little at the restaurant. Those who spent a lot at the grocery store spent a lot at the restaurant. So I want a metric that tells me the direction of the relationship. And in this case, it's a positive relationship. The more you spend at the grocery store, the more you spend in a restaurant. And I also want a sense of the strength of the relationship, right? If everyone fits relatively on this straight line, I have a fairly good relationship. And it's very clear. You spend $50 more at the at the grocery store, you're going to spend roughly $50 or more dollars more at the restaurant. The relationship can stay positive, but as the points start to separate from the straight line here, then it means that it's the relationship, although a positive relationship, is getting weaker and weaker. And once that relationship turns into a ball, right, the dots are just scattered around like a shotgun thing, that means I have no relationship. Okay. So the direction of the relationship, positive or negative, and the strength of the relationship. So the correlation coefficient ranges from -1 to +1. -1 means it's a perfect negative relationship. The higher the score on the x-axis variable, the lower the score on the y-axis variable, right? So the line points down. A positive relationship is +1. And a perfect positive relationship is a value of 1. Everyone fits on a straight line. A correlation coefficient of 0 means there is no relationship at all. And then everything in between is a relationship, but it differs in strength. Okay. The correlation coefficient, I'm not going to, for this course, you don't have to kind of know the calculations, you just have to kind of know what it is. What I do is I standardize each score. So for each restaurant score here, I take, for the food store, I take the score of 45, subtract the mean, and divide by the standard deviation. And that gives me a standardized score. And when I do that for each of them, this is the standardized score. I've applied this formula here, the Z for food, 45 minus 163 divided by 78. 75 divided by 163 minus 163 divided by 78. Those are standardized. That produces standardized scores. They're standardized scores and given the special letter Z because the mean and standard deviation is always going to be 0 and 1. So a mean of 0 and a standard deviation of 1. So I convert my two variables into their standardized scores, their Z scores. Z for food, Z for restaurant. And the correlation coefficient is simply the product of the Z-scores. I multiply the Z-score for the food and the Z-score by the Z-score multiplied by the Z-score for the restaurant. I get that product, do that for all 10 people, sum those values up, and then divide by the number of people, and that is my correlation coefficient. And in this case, the correlation coefficient is 0.99, or almost perfect. A correlation can only be as high as 1.00. If you get a correlation of, say, 1.3, someone's kind of like messing with you because it just doesn't, it's impossible. It can't happen. It can't happen. Okay, and in this case, all the points are on pretty well a straight line. Straight line is pointed up, but not vertical. And I have a R, my correlation coefficient, which is always given the letter R, is equal to 0.99, or a near perfect positive correlation. Okay. Now, with correlation, I cannot infer causality because there could be other, it could be a spurious correlation, or it could be due to an intervening variable or a third factor that's explaining the relationship. So in this case, I can't say that people who spend more on weekly restaurant spending causes them to spend more in restaurants, right? There is not a causal relationship between the two variables. Why? Because when I add in the country of residence for the person, and I figure out how much their average food, what the cost of food is in those countries benchmarked to the United States, in Tunisia, the groceries are on average 67%, food costs are 67% lower than the costs in the US. In Switzerland, the food costs are 79% higher than the food costs in the United States. The United States is the benchmark. And Canada and Australia are very close to the US in terms of our food costs. So the reason why food store bills, the food store cost is positively related to the restaurant cost, right, 45.36, 305, 200, is because, not because weekly food store spending is correlated or is causing restaurant spending. It's because of a third variable, that in Switzerland, restaurant food store grocery costs are high and restaurant costs are high because just in general food is more expensive in Switzerland. So I can't infer causality from correlation. Okay. So I can have a perfect positive correlation is all the points fit online. So if my instrument has test retest, in terms of, I use let's say I'm doing the let's say that's the procrastination scale. I give a group of people the procrastination scale one day, and then a week later, a month later, I give them the procrastination scale again, and they've gone on that. So, and what I would expect, if my instrument is reliable, then if they score high the first time, so this is test, they should score high on the retest. The retest would be the XY axis, the X axis would be the test. And if my test has perfect reliability, then everyone should fit on a straight line. If they scored if they scored low on the test, they should score almost identical. They should score identically on the retest, and that should happen for everybody. Once I start having problems where people aren't quite getting the same consistent result from one test administration to the next, my reliability starts to lessen. And I could get to the point where my instrument, my procrastination instrument, where there's no relationship from one test to the next. So here's a person here who scores moderately high on the test, but scores super low on the retest. Well, that shouldn't happen, and vice versa. I could have someone who scores high on the, or scores low on the pretest, gets a 0, but scores super high on the retest. If my results are flying all over the place in terms of someone scores low on the test and high on the retest and vice versa, my instrument has no reliability. And if my instrument has no reliability, it clearly has no validity, right? There's no consistency. Okay. So here's an example of a perfect positive correlation. Don't worry about the calculations. Here's a perfect negative correlation. Negative correlations you should not see in reliability research, right? So I'm just demonstrating it here. for reliability, it should always be a positive correlation, right? You score low once, you should score low the second time. Score high the first time, you should score high the second time. So for reliability, it should always be a positive correlation. But just in general, for the correlation coefficient for explanation purposes, this is what a negative correlation looks like. Okay. And there's a perfect negative correlation. Here's zero correlation, no relationship. And just only one thing is I did it for the population divided by n. If it's a sample, you divide by n minus 1. And if you're looking through textbooks, oftentimes you'll see the computational formula. I don't know why people do that anymore, but because in the old days, like when I was a young pup in university and I had my slide ruler and I had my my chalkboard with my little chalk slate thing, and they had a nice wood stove in the classroom. Then I would do my calculations by hand. I would use the computational formula, reduces rounding error, and is generally row by row easier to do because I'm just kind of like creating sums, not having to do the funky Z test and stuff, or Z scores. So the computational formula is just computationally easy to do, but we don't do calculations by hand anymore, so I've never understood now why textbooks even show it anymore. Oh, excuse me. My yawn I'll take out of the video. Okay. One other thing we want is consistency of people's responses across the items on a multiple item measure. So key thing here is all the items on such measures are supposed to reflect the same underlying construct. So people's scores on those items should be correlated with each other, roughly, right? It doesn't have to be perfect, but if you're using a Likert, for example, if you score on a 4 on one, you should score on a 4 on another. Or you should be consistently scoring 4s, for example, across an instrument, right? That's assuming that what's your underlying construct. So if I start getting into subscales and sub-constructs, right, this is where this doesn't really work very well. So in terms of internal, the test retest is something in terms of just overall test score. Internal consistency, you can do it split half reliability, right? You just basically use randomly, or you can take the first half of the instrument, compare it to the second half of the instrument. So the first 15 items, the second 15 items. Create a score for the first half, create a score for the second half, and then calculate the correlation coefficient. So the score for the first half of the test, for the first 15 questions, should correlate with the score for the second half, or the 15, questions 16 through 30. Right? So that's split half reliability. You can split it in half, first half, second half. You can do odds and evens, but what you're going to do is you're going to create a score for the odd items and a score for the even items. And if your test has internal consistency or internal reliability, then the two should correlate very well. Cronbach's alpha, what it does, it creates all possible split half correlations for a set of items. So if there were 250 ways to split a set of 10 items into two sets of 5, Cronbach's alpha will be the mean of the 250 split half correlations. So what Cronbach's alpha does, it says, okay, well, if your items score fairly consistently, and they don't have to be perfect, then Cronbach's alpha is a funky and math-intensive way of producing all possible combinations of if you split the test in half, it produces all combinations. So if you've got 4 items in your test, your combinations in terms of split half are combining items 1 and 2, items 3 and 4. You can combine, then do a split half again for item 1 and 4, 2 and 3. 1 and 4, 2 and 3, 1, 2, 3, 4, and then 1, 3, 2, 4. So I think there's 3 combinations on there. My head's getting a little dizzy. So you can then look at internal consistency both with the split half, or you could do Cronbach's alpha by churning out all possible split half combinations to calculate the average split half, which is a much more calculation intensive, and is your standard basically measure of internal consistency, right? Your items are consistently measuring the same thing, and people are responding with similar patterns in terms of across, in this case, the split half. Okay. And we talked about inter-rater reliability, which is more on a qual side. I remember years ago when I was a grad student, I was taking a dev site course at grad school. I ended up part of a study on requesting behavior with toddler children. And us in the class, in this grad class, we had to watch hours of video, family recordings in people's homes of kids, little toddlers running around and looking at their requesting. They're not verbal yet. They weren't talking, but they could still request behavior. Like, you tug on mommy and point at something to get, they want that toy off the shelf or something. So we had to have we had a coding manual and a coding scheme, and we had to code them with these codes. And then, the professor who was running the course, she then would do the inter-rater reliability to see, well, did I code it similarly to Betty Sue, who also coded it, and Bobby and Sissy and Lawrence. So yeah, and that's something more for on the qual side. Okay, so last bit for today is just a little